Okay, in this video, we're going to work problem 5.90 from our textbook, what is it, Fundamentals of Fluid Mechanics by Munson et al. And this is a turbine example as follows. We're told that we have a radial turbine, and this one's a little different than what we're used to because on this one, the flow is actually coming in from the outside as opposed to what we're used to, where it comes in at the middle and it moves outward. But in this case, we have the flow coming in like this. It goes through the turbines and the turbine blades, and it's turned and it comes out something in that direction. We're going to get to the numbers here in just a minute. We're told something about the various angles of the blade geometry, and we know something about how the fluid is coming in. But before I do that, we're going to need to know that if we look at this thing from the side, it looks like this, of course, and the flow is coming in from the outside and comes out like this, which is opposite of the direction that we're normally used to, but that's okay. We can deal with it. The problem with this problem, or one of the things we have to find, is this dimension b. We're not given b. We're told what the flow rate is, and we're told a lot about the angles of the flow, but we're not given b. And so we're going to have to think a little bit about how we're going to work backwards from the way that we normally do in order to solve this problem. Now let's fill in the numbers that the book gives us about the flow. I'll do that in blue here again. We're told that relative to the blade, or relative to the moving rotating reference frame, that W comes in with an angle of 60 degrees to the tangential coordinate. We're told that it leaves with an angle, let's erase this one here to get it out of the way. We're told that it leaves with an angle of 120 degrees. That's W, that's the relative fluid vector. We're told that the vector in the absolute frame, V, comes in with an angle of 20 degrees. Let's see, we're told some more things about this. We're told that the radius of the inner diameter is 2 feet, and we're told that the radius of the outer, I just said diameter, the radius of the outer of what turns out to be the inlet in this case is 4 feet. We're told that it rotates in a clockwise direction at 50 RPM. And I think oh yeah, we're told that the flow rate, Q, is 20 cubic feet per second. So let's see. The water turbine wheel rotates at the rate of 50 RPMs in the direction shown. The inner radius of the blade is 2 feet. The outer radius is 4 feet. We have both of those. The absolute velocity at the turbine rotor entrance makes an angle of 20 degrees with the tangential direction. The inlet blade angle is 60 degrees relative to the tangential direction. The blade outlet angle is 120 degrees. The flow rate is 20 feet per second. For a flow tangent to the rotor blade surface at the inlet and the outlet, that means that W is tangent, has the same angle as the rotor blades. Determine an appropriate constant blade height B, and then we also have to find the corresponding power available at the rotor shaft. So we need to find B, and then in part 2 we need to find the work being done, or the power being done at the shaft. Now this is one of those problems where it's not it's not obvious the direction that we go. We're used to using the formula, for example, the flow rate is equal to the area of a boundary, whether it's the inner boundary or the outer boundary. Let's just say 2 pi, and we'll just use a generic r, times b times some velocity in the radial direction. And I'm going to put this in quotes because we haven't dealt with the plus or minus nature of this. But we're used to knowing this stuff on the right, or at least being able to figure out this stuff on the right and going this direction. Or sometimes we're given Q and we want to find VR. In this case, it's a little bit more difficult because we want to find B, and it's not super easy to figure out what we want to do. We know that we're going to use this relationship. We know that somehow these angles are gonna help us out. But the way to attack most of these problems, and the way to attack this one, is to write down what you know. Write down what you know in vector about your vector systems, and write down and make your vector triangles. So you can write your vector triangles, write down your vector components, and hopefully it should be clear how to go on from there. And I say that with a grain of salt because, of course, the first time that I worked this problem, it wasn't super clear how to attack it. Turns out we attacked it correctly. It just wasn't obvious. So let's look at the outer boundary, which we're going to subscript everything at the outer boundary as 1, and everything at the inner boundary as 2, and that's opposite of normal. But in this case, the inlet is boundary 1, which is the outer boundary, and the outlet is boundary 2, which is the inner boundary. Paradoxical, I know. But we can draw our vector triangles, and let's see, I used red above for V, so we know that V is coming in like this, and that this makes an angle of 20 degrees. We know that W is coming in like this, and this makes an angle of 60 degrees. And we also know that U, because this thing is spinning clockwise, we know that U is off in this direction, and we'll draw it like that. Oops, I forgot to label W here, so let me label W. And we know that we always specify the absolute velocity to be the velocity of the reference frame plus the relative velocity. And we can write out the components, and we can write that VR is equal to WR because there's no radial component of the U velocity. And we know that V theta is equal to U theta plus W theta. Now, let's see, let's be sure to get our coordinate system here because we're going to need this. R hat is going to point in the outward direction, and as normal, as usual, theta hat, the tangential unit vector, is going to point to the left in this particular case. Now, we also know from the geometry that tangent of 60, sorry, not tangent, sine of 60 degrees for our W is going to equal, let's see, 60 degrees is here, so opposite over this, so it's going to be equal to WR over the speed W, but because WR is going to be pointing inward, we're going to get a minus sign here. Cosine of 60, similarly, is going to be minus W theta over W. And we can do the same thing for our absolute velocity. We get sine of 20 equals minus VR over over V, and cosine of 20 equals minus V theta over V. Keep in mind that these W's and the V's in the denominator are speeds, so they are always going to be positive scalars. And so we have to use what we know about the relationships, about the way we've drawn our vectors here to know that all of these are going to be minuses, because when we plug them into the vector form, we want WR to be, so sine 20, cosine 20, sine 60, cosine 60 are all positive. W is all positive, but we want WR to be negative because it's coming inward. We want W theta to be negative because it's going to the right. And same for VR and V theta. Now we know that the volumetric flow rate, Q, is going to be given by, and if we do it formally, we could say the integral over the inlet of V dotted with n hat times the area of the inlet. And in this case, that's going to give us, for a uniform flow, steady in the mean, all of the normal assumptions that we make, that's going to give us the area, which is 2 pi r1, where r refers to the one subscript refers to the outer boundary, times b, the thickness, times v dotted with n, which is just going to be VR, or in this case it's going to be minus VR, because Q is always a positive number, and VR is going to be a negative number because V is pointing inward. So we put the minus sign here to make sure that we have Q being positive. So we also know that VR is equal to WR, so we can alternatively say 2 pi R1B times minus WR. Let's write the Q's there. So we're looking for B. We know what Q is. We know 2 pi R1, of course, but we don't know what either VR is or WR is immediately. We're going to have to figure that out from the geometry and from our vector triangles up here. The best way to do that, well, I don't know if it's the best way to do this, but after thinking about it a little while, this is what I came up with, which is we know that, let's see, let me switch to blue here for a second. If we divide this equation, the sine 60 equation, by the cosine 60 equation, we just get tangent of 60 is equal to, the w's cancel, so we get WR over W theta. And if we do the same thing for the v's, we get tangent of 20 equals VR over V theta. Right. But we know that VR and WR equal each other. So what I did is I wrote this as, well, VR, I substitute WR, so we get a WR on the top. And in the denominator, V theta is equal to U theta plus W theta. So now we have two equations. This one here, tangent 20, is equal to this mess on the right-hand side. And we also have this one here where tangent 60 is equal to this mess. But both of them have a value for WR, which we know. Sorry, we don't know, but we can set those equal to each other, and then we can solve for W theta, because then the only thing we'll need is we'll have W theta, which we don't know, but we'll have U theta in tangent 20. So let me show you what we're going to do here. We're going to say WR here is equal to tangent 20 times U theta plus W theta. And we're going to take this one here and we're going to say WR is equal to W theta tangent 60. But of course WR is equal to WR. So now we can take this and combine and separate and rearrange. And I think you will find that we have on the right-hand side, what do we have on the right-hand side? We have U theta tangent 20. And on the left-hand side, we have W theta times tangent 60 minus tangent 20. or W theta equals U theta times tangent of 20 over tangent of 60 minus tangent of 20. Sorry. And so now we know U theta because we're told we're told everything we need to know about the geometry and the rotational speed. Obviously, we can calculate tangent of 20 and tangent of 60, and so we can figure out what W theta is. So U theta is going to be equal to 2 pi times 50 RPM divided by 60 seconds in a minute times the radius at that point, which is 4 feet. And let's say there's a 1 over seconds in here somewhere. So that's U theta, which for future reference is going to be 2 pi 50 divided by 60 times 4. And that's going to be 20.94 feet per second. Except that it's going to the right, so it's going to be a minus, it's going in the negative theta hat direction, so we get a minus sign there. And all of that times tangent of 20 divided by tangent of 60 minus tangent of 20, which all that, I get 0.266, so we multiply those together, and we get that W theta is equal to minus 5.572 feet per second. And I'm carrying out the decimal places because we're going to need them for this particular problem. So we know W theta, which means we know WR is equal to W theta times tangent of 60. And so that's going to be equal to minus 9.65 feet per second. So we can substitute this into this and rearrange, and we get B, the thickness of our blade, is equal to Q over 2 pi R1 times minus WR. And I'm not going to write that out, but I get, let's see, let me store that value. I get 20 divided by 2 divided by pi divided by 4 for R1 and divided by 9.65, and I get that to be 0.0825 feet. This kind of bothers me because if you convert that to inches, that's just about 1 inch, which is pretty thin for our fairly large-sized turbine. But if you take this, and you can go ahead and try it, but if you take what we know for B and work the normal direction that we work for these problems, so given Q, find WR, given WR and the angle at which the blades are tilted, and do all the calculations going backwards, you'll find that indeed you end up with 20 cubic feet per second, or whatever value you need for V, whichever way you're going to do it. So by my calculations, this is the correct number. All right, so now we need to find the power. And to find the power, we know that the power is given as the product of the torque with the angular velocity. And we know that the torque is given from the conservation of angular momentum, which for a steady in the mean uniform flow system is given as the integral over the control surfaces of the density times r cross v times v dotted with n hat dA, which we know is going to be, we're going to divide into the inlet and the outlet portions for this this turbine. And since we know most everything for the outer radius, we're going to start there. Let's see. Remember our vector triangles here, and we know our vector relations here. And so at the inlet, this is going to be equal to the integral over the inlet is rho, well, I'll just rewrite it for a second here, r cross v times v dotted with n hat dA. And so that's going to be, so for the uniform flow, that's going to give us, as we're used to, integrated over the area. It's going to be the area, which is 2 pi r1b of, let's see, the r crossed with v, so we're going to have r1 r hat cross v times v dotted with n hat, but n hat in this case is going to be the r hat outward pointing vector. And so we see that we get 2 pi r1 b. Let's see, for v we only need the theta component. R cross v gives us a z, so we get r1 times v theta, and I'm going to put a comma 1 here because we're still talking about the inlet. And then here we get v dotted with r, so we're just going to get a vr out of that. vr, and all of that has a z hat component because of our cross product here. We already know most of these, but we can write the area and VR. We know all that's equal to minus Q, the flow rate. Oh, I left out a density here. So we have a density here, and we have a density here. So we have Q times rho, which is the volumetric flow rate, times the density, which we could write as the mass flow rate if we wanted to, times R1 V theta 1 z hat. But this is the contribution to the torque, and so we could dot it right now with the angular velocity, and that might be easier. So let's write the work due to the momentum transfer at the inlet is equal to the torque at the inlet dotted with the rotational speed. So that's going to be equal to minus Q. Now let's put the rho out here. Minus rho Q R1 V theta 1 z hat dotted with omega, which is omega z hat. But we know that R1 omega is equal to u theta, so this becomes minus m dot. I'll just go ahead and make this the mass flow rate here, times u theta times v theta at the inlet. So if we plug in some numbers, we get, well, now we got to go back to density because we don't know the mass flow rate precisely. We get 1.94 slugs per cubic foot times Q is, oh sorry, we got a minus out here, don't forget the minus, times Q is 20 cubic feet per second, and then it's going to be times U theta, but which, if you remember, is minus 20 something, right? Where did u theta run off to? Here it is, minus 20.94 feet per second. Minus, what did I say, 20.94 feet per second, times v1 theta, which is also a negative number, which is, we have not calculated v1 theta, have we? No. So we still need v1 theta, and it's probably best if we do it right here, because we know that v theta is equal to u theta plus w theta, so that means that v1 theta is equal to minus 20.94 plus w theta, which is minus 5.572, and all that is equal to, well, that is equal to, plugging in my calculator here, 5.572, I get 26.516, gotta be precise, feet per second, 26.516, whoops, minus. So here we multiply this by minus 26.52 feet per second. Cancel the cubic feet here and the cubic feet here, and we get, all told, I get is equal to minus 21,550 slug feet per second squared times feet per second. I wrote that intentionally like that because this is a pound force, and pound force feet per second, and everybody knows that there are 550 horsepower in a pound force foot per second. So if we divide 21,550 by 550, we get, this is equal to minus 39.2 horsepower. This is good because it's negative, which means that we do have a turbine, so we're extracting energy from the flow. And you could imagine that if v theta were 0 at the outlet, so if the flow at the outlet were entirely radial, we'd be turning the flow, and we'd be doing it in such a way that we would be, again, we'd be extracting energy to get a turbine. So we're happy with the negative number. What we're not happy with, I must say, is the magnitude. We have 39.2. The back of the book has 39.6. But this is only the work done at the inlet. This is only the work done across region 1. And I'm pretty sure that when we do it across region 2, we're going to get more than just 0.4 horsepower. I've looked through this. I cannot find a mistake. I've also gone and worked backwards and gotten the given this much power, given this size B, worked backwards and gotten the same amount. So I wouldn't be surprised if the book is actually they only calculated for the inlet and not the outlet as well. You're all welcome to check my work. The thing to note is that because I kept track of my because I kept track of, I did everything in vector terms and my dot products and my cross products, that the sign falls out. So the negative sign falls out on its own. I don't have to do any too much thinking about what's pointing in the direction of what in this case. And I like that. You may like to do the rules of thumb instead. That's your choice. The big thing is to look at it at the end and say, look, if this were a positive number, we'd be doing work on the system. And clearly, with the way that we're turning the flow, we're not doing work on the system. So let's look at section 2. Actually, you know what I'm going to do? I'm going to stop this video and upload it, and then I'm going to do section 2 as a separate video because this one's getting a little bit long. So look for video number 2 here in a few minutes.